each conductor has a magnetic field. Now, don't you expect that there will be a force between these two conductors? Well, let's look at the force between two parallel wires that carry a current. Now, here I have two parallel wires, each carrying a current I, like this. There are two parallel conductors carrying a current I in the same direction. And if you now apply the law that you've learned, what is the direction of magnetic field due to the lower wire? If you use your right hand rule, the field will go into the board below the wire and out of the board above it. Same in here, into the board below the wire and out above it. And so, if you notice, the direction of the field in between, due to the lower wire, the field comes out of the board. Due to the upper wire, the field goes in. And as a result, the field in between the two wires is very weak. And the field outside the two wires is very strong. So you would expect the strong field will push the two wires into the region of weak field. So, if there are two parallel wires carrying current in the same direction, what kind of force would you expect between the two wires? You would expect that there will be an attraction between the two wires. Well, so as a result of the field due to each, there will be a force between them. The strength of the magnetic field produced by each wire is given by, now, you remember that equation? What's the equation for the strength of the magnetic field produced by a wire that carries a current I? Is mu0 over 2 pi times I over R. So this wire will produce a field mu0 over 2 pi times I over R here, and this wire will produce the same field where the other wire is. Now, let me see if I can show you that on a website. As I illustrated earlier, if the currents are in the same direction, the field due to these two in between, if you notice, they are in the opposite direction, they cancel. So there are strong fields outside and a weak field inside that will produce a force that pulls the two wires together, or it is an attractive force. On the other hand, if equal currents are in the opposite direction, this time one wire carries current outwards and the other carries current inwards, you can see the field in between is very strong and the field outside is weak. Therefore, the strong field will repel the two wires. So, if you want to put it together now, you can now say if two wires carry currents in the same direction, there will be a force of attraction. If two wires carry currents in the opposite direction, there will be a force of repulsion between them. If you remember the expression for force exerted by a current carrying conductor that we discussed in the last lesson, we can say the force exerted by the bottom wire on the top wire will be IL times B, where I is the current, L is the length, and B is the magnetic field produced by the bottom wire at the top wire. So the force exerted by the bottom wire on the top wire is ILB, and therefore what is the force per unit length of the wire? If you now divide both sides by L, I get force per unit length will be I times B. And that will be, B we know is mu0 over 2 pi times I over R. Therefore, force per unit length of a wire in this case is I times mu0 over 2 pi times I over R. and I get multiplied. We can write mu 0 over 2 pi times I squared over r. Now, as a result, each of the wire will experience a force due to the magnetic field of the other, and we explained how that happens. When the two wires carry currents in the same direction, there is a force of attraction, and when the currents are in the opposite direction, there is a force of repulsion. And I explained how that phenomenon occurs. Now, if the current in the left wire is I1 and the current in the right wire is I2, instead of the current being the same, if they are different currents, I1 and I2, then the force per unit length will be mu 0 over 2 pi times I1 I2 over r. If the currents are the same, both will be I, and we have I squared there. But if the currents are different, then this will be the equation. Alright, let's do a different problem. A horizontal wire carries a current of I1 equal to 80 ampere. A second parallel wire of mass per unit length of 0.12 gram per meter is situated 20 centimeter below it. What must be the current on the second wire so that it does not fall due to gravity? Well, we have a horizontal wire carries a current and a second wire is below it. Now, the situation here is the force of attraction between the two. There will be a force of attraction when the currents are in the same direction. The force of attraction between the two must balance the weights so that this will be suspended in the air due to that force. So what must be the current on the second wire so that the second wire will not fall due to the force of gravity? Well, this is a situation we have. We have a horizontal wire that carries a current of 80 ampere. And there is a second wire below it, a distance of 20 centimeter. We need to find the current in this wire such that the force of attraction between these two wires is exactly balanced by the weight of the bottom wire. Alright, we got I1 equal to 80 ampere. If I2 is the current in the lower wire, then what is the force per unit length on the lower wire? What's the equation for force per unit length? It's mu 0 over 2 pi I1 I2 over r. We got all these values except I2, is that right? Alright, and that will be mu 0, of course, is 4 pi times 10 to the negative 7. I1 is 80 ampere and r is 0.2 meter, and that's equal to 8 times 10 to the negative 5 I2. This is the force per unit length, and this force per unit length must be equal to the weight per unit length of that wire. You are given the mass per unit length, therefore weight per unit length will be mass multiplied by g. That will be 0.00118 Newton. We can now take the weight per unit length of this wire and equate it to force per unit length, and we can calculate I2. What is therefore I2 equal to? I2 equal to 15 ampere. Well, we can use the concept of force between two parallel wires for giving a definition for the ampere. In fact, the original definition of ampere is obtained from such a situation. The force between two wires is used to give an exact definition for ampere, the unit for measuring current. Now, the equation for force per unit length of a wire when current flows in the same direction in two parallel wires separated by a distance r is, well, you know that, F over L, force per unit length, is mu 0 over 2 pi I1 I2 over R. Now, we're going to use this situation to obtain the definition of the ampere. What is 1 ampere? Suppose I1 is 1 ampere, I2 is 1 ampere, and R is 1 meter. So let's make that assumption. When I1 equal to I2 equal to 1 ampere and R equal to 1 meter, mu 0 we know is 4 pi times 10 to the negative 7. Now, if you use these values, what will be the force per unit length equal to? I replaced I1, I2 by 1 ampere, R by 1 meter. Of course, this is mu 0. And what is the value of force per unit length here? It is 2 times 10 to the negative 7 Newton per meter. Alright, can you now use this to define the ampere? What is the definition of ampere? We said if I1 equal to I2 equal to 1 ampere. So 1 ampere is the force. 1 ampere is defined as that current when flowing in each of two long parallel conductors separated by a distance 1 meter results in exactly a force of 2 times 10 to the negative 7 Newton per meter of length of each conductor. So, a current that flows in two parallel wires that are separated by 1 meter, that results in a force per unit length of this much, is what we call 1 ampere. And that is the original definition of the ampere.